All the loads that we have considered up to now have been concentrated loads, that is, loads applied at one point of the body. Of course, this is an idealization, and loads are really applied over certain regions of the body, or in the case of body forces like gravity, they're applied at every single point of the body. So now we are starting to consider also distributed loads. I know you have seen distributed loads before in your basic introductory classes in physics, so let's review a few basic concepts. The typical picture that you are given when you first start considering distributed loads is to consider a plank loaded by something like sand or bricks. So you have your plank, and on top of your plank you have, say, an even distribution of bricks, all at the same height. So in this case, you can see that the plank does not have a concentrated load acting on it, but rather there is a certain distributed load acting on the plank, coming from the weight of the bricks. So say, for instance, that the bricks on top of each meter of the plank weigh 1000 newtons. Then what the bricks are doing is applying a distributed load on the plank equal to 1000 newtons per meter. So now if we want to calculate what is the total load that the bricks exert on the plank, we need to multiply the 1000 newton per meter by the length of the plank. Say that the plank is 5 meters long, then the total weight that the bricks apply to the plank, the total load applied by the bricks, is 1000 newton per meter times 5 meters, and that is 5000 newtons. Now this calculation was very simple because the weight of the bricks was uniformly distributed along the length of the plank, so we can simply use a multiplication to obtain the total load. In general, things may be more complicated and your distributed load may not be uniform. In these cases, what you need to do is use the concept of integration. Well, you will obtain the total load by integrating the distributed load over the length of the plank. So, to see how this works, let's start from the very simple case of a uniform distributed load. We have already calculated the total load for this case simply by multiplication. Let's see how we obtain the same result by using integration. The first thing that we need to do is to introduce a function that gives us the magnitude of the distributed load as a function of position along the length of the plank. So let's introduce a Cartesian coordinate axis x, and let's say that this end of the plank is A and this other end is B, so that this is xa and this is xb. So in general, the magnitude of the distributed weight applied by the bricks on the plank will be a function of position. So let's call this function lowercase w of x. This will be, of course, in units of newtons per meter. In our case, our distributed weight is uniform, so w of x will be a constant, will simply be equal to w0, which happens to be 1000 newtons per meter. So let's plot it right here, right under the plank. So if w0 is the weight of bricks per unit length, the weight of bricks over a small differential length dx is going to be simply equal to w0 times dx, which is the area of this small rectangle. If you want to sum the contribution of the weight of the bricks between xa and xb, you need to keep summing the areas of these rectangles as you sweep along the length of the beam from xa to xb. So the total weight of the bricks is going to be the total area under this curve. The area underneath w of x between xa and xb is the definition of the definite integral of w of x between xa and xb. So we can calculate the total weight of the bricks as the integral between xa and xb of w of x in dx. And of course, in our case, w of x is simply w0. So the total weight comes out to be the integral between xa and xb of a constant w0 in dx which simply is equal to W0 times the integral of dx between xa and xb, and that's simply equal to W0 times xb minus xa, and xb minus xa is the length of the plank. So we go back to obtaining the total weight of the bricks simply as W0, that was 1000 newtons per meter, times the length of the plank, which is 5 meters, and we are back to 5000 newtons. So how does it work now if instead of having a uniform distributed load, we have a distributed load whose magnitude changes with position? So let's say that instead of having bricks, we have sand piled up on our plank, so that we have a higher magnitude of the distributed load in the middle of the plank, and then it linearly goes to 0 towards the edge of the plank. So the magnitude of the distributed load, the weight of sand per unit length of the plank, is still our W of x, and is still in newtons per meter. It's just that now our W of x is not a constant. We can plot it on this axis down here, and we see that W of x starts at 0 at x equal xa, increases linearly to a maximum value in the middle of the plank, and then decreases again linearly as x goes to xb. So let's call the middle of the plank C, so that this is xc, and let's call the maximum magnitude of weight per unit length wc, because it happens at point C. So now we can define the function w of x in terms of these coordinates. So we can write that between a and c, w of x is going to be wc that multiplies x minus xa over xc minus xa. So doing this, we see that this is going to be a function that is linear in x, increasing with x, is going to be 0 when x is equal to xa, and is going to be wc when x is equal to xc. Now on the other side, when x is between xc and xb, then w of x is going to be again wc, but now it's going to multiply xb minus x over xb minus xc. Because we see that with this kind of function, the function is linear but decreasing with x. It is 0 when x is equal to xb, and is wc when x is equal to xc. So this is going to be our w of x. Now, if I want to calculate the total weight that the sand exerts on the plank, all what I want to do now is do the same integral of w of x between xa and xb. Why is that? Well, if I take any little elemental segment of the plank dx, you can see that the weight of the sand over the little element dx, it's again w of x, that is at that x, times dx. So if I want to sum all these contributions between xa and xb, I'm back to having the definite integral of w of x between xa and xb. Now, for a function like this, you have to be careful, because since the function is discontinuous, then you need to split the integral. So if you want to calculate this integral, you have to write it as the integral of w of x between xa and xc plus the integral between xc and xb. And in this first part of the integral, you use this expression for w of x, and in this other integral, you use the second expression. So this is what the whole integral is going to look like when you substitute the value of w of x. And when you calculate it, you're going to find that this integral is simply going to give you xb minus xa times wc divided by 2. How do I know this without even doing the integral? Well, I know that this integral is the area under this curve. So this is a triangle, this is the base of the triangle, this is the height of the triangle, and the area of the triangle is going to be base times height divided by 2. But if you do your integrals with the w of x as a function of x, you should find exactly the same result. So I'm sure now that as you watch this video, you're wondering, what are we doing with these planks, the bricks, the sand, when really we should be talking about axial loading? Well, the answer is that I just wanted to remind you how do you integrate distributed loads, and it's easier to visualize them as weights on a plank. So this is only part 1 of the story. It's time for you now to move to part 2.